Our cosmic origin story might be built on a fundamental oversight. We have a detailed timeline for the universe, from the Big Bang to the galaxies we see today, but major pieces of the puzzle are still missing. This video will reveal how a single, ancient phenomenon could solve multiple cosmic mysteries at once. The key lies in a hypothetical class of objects called primordial black holes. These are not the black holes formed from dying stars. Instead, they are relics from the universe's very first second, born from wrinkles in the fabric of space itself. If they exist, they could force us to rewrite the history of everything, challenging our models of dark matter, the rapid birth of supermassive black holes, and even the nature of the Big Bang. How much of what we think we know is waiting to be overturned? To understand the potential revolution, we first need to see the story it aims to rewrite. The standard cosmic timeline is a magnificent epic, pieced together from decades of observation and theory. It begins with the Big Bang, a moment of incomprehensible energy that birthed space and time themselves. In the tiniest fraction of a second, a period called cosmic inflation is thought to have stretched the universe from subatomic to cosmic scales, smoothing it out and planting the seeds for all future structure. As the universe expanded and cooled, a primordial soup of particles began to form. Within the first few minutes, during an era known as Big Bang nucleosynthesis, the lightest elements like hydrogen and helium fused into existence, setting the chemical foundation for everything to come. For hundreds of thousands of years, the universe remained a hot, opaque fog of plasma, where light was constantly scattered by free electrons. Then, around 380,000 years after the beginning, a pivotal event called recombination occurred. The universe cooled enough for electrons to combine with atomic nuclei, forming neutral atoms. This allowed light to travel freely for the first time. That first light, now stretched into microwaves by the universe's expansion, is the cosmic microwave background radiation we detect today, our oldest snapshot of the cosmos. From this point, the story is one of slow, gravitational patience. Tiny quantum fluctuations from the inflationary era, imprinted as minute density variations in the cosmic microwave background, served as the blueprint. Over hundreds of millions of years, gravity patiently pulled matter toward these slightly denser regions. Gas collected, condensed, and eventually ignited the first stars, ending the cosmic dark ages. These stars gathered into the first small galaxies, which then merged over billions of years to build the grand spirals and ellipticals we see today. It is a coherent, elegant, and remarkably successful narrative, supported by a vast web of evidence. Yet, for all its successes, this standard model contains profound and puzzling gaps. Two stand out as particularly glaring. First, we have the mystery of dark matter. All our observations of galaxies and galaxy clusters show that there is far more gravitational pull than the visible stars and gas can account for. Something invisible, something that does not interact with light, makes up about 85% of all matter in the universe. Our timeline describes how normal matter clumped together, but it is completely silent on what this dominant dark component actually is or how it behaved in the early universe. Second, there is the baffling speed of the first supermassive black holes. We now see these monsters, weighing billions of times the mass of our Sun, at the centers of galaxies when the universe was less than 1 billion years old. In the standard slow and steady model of gravity, there simply does not seem to be enough time for such enormous objects to grow from the collapse of the first, relatively small stars. It is as if we walked into a forest and found fully grown, ancient redwood trees where, according to our gardening schedule, there should only be seedlings. These are not minor details, they are fundamental cracks in the foundation of our cosmic story, hints that a crucial ingredient may have been missing from the recipe all along. This missing ingredient could be hiding in plain sight, not as an exotic particle, but as a shadow from the very dawn of time. We call them primordial black holes. To grasp why they are so revolutionary, you must first forget everything you know about how black holes are made. The black holes we have confidently observed, like the one at the center of our galaxy, fall into two familiar categories. Stellar black holes are the ghosts of massive stars, formed when such a star exhausts its fuel and collapses under its own immense gravity. Supermassive black holes, millions to billions of times heavier than our Sun, sit at the hearts of galaxies, though their exact birth process remains one of astronomy's great puzzles. Primordial black holes are something else entirely. They are not the end result of a star's life, but rather a potential starting point for the universe itself. Theorists propose they could have formed in the first chaotic moments after the Big Bang, when the entire cosmos was an unimaginably hot, dense, and turbulent sea of energy. In such extreme conditions, random quantum fluctuations could have created pockets of space that were significantly denser than their surroundings. If one of these ultra-dense regions contained enough mass energy within a small enough volume, it could have directly collapsed, bypassing the need for a star altogether. It would have simply become a black hole, a knot of pure gravity woven into the fabric of the newborn universe. The timing of this collapse is key, and it leads to a fascinating possibility. Because these black holes could have formed at different instants in that first second, their masses could be almost anything. A black hole born in the very earliest, most energetic moment might have the mass of a small asteroid, compressed into a space smaller than an atom. One that formed a fraction of a second later, as the universe expanded and cooled, could possess the mass of a star or even 1,000 suns. This means the cosmos might be quietly filled with a hidden population of black holes of all sizes, ancient relics that have been drifting through the darkness for over 13 billion years, completely invisible unless they interact with something. They would be cosmic fossils, offering us a direct glimpse into conditions we can never recreate. So while we have been looking for dark matter in the form of undiscovered particles, the answer might instead be these gravitational ghosts, born from the wrinkles of creation itself. The link between these ancient black holes and the universe's first moments hinges on a key idea: cosmic inflation. This theory proposes that a fraction of a second after the Big Bang, space itself underwent a period of exponential, faster-than-light expansion. It is a concept designed to solve several puzzles about the large-scale smoothness and geometry of our cosmos. But within this theory lies the potential mechanism for creating primordial black holes. During inflation, the universe was not perfectly smooth. At the quantum level, empty space is never truly empty. It is a seething foam of virtual particles popping in and out of existence. These are temporary quantum fluctuations. Normally, they vanish as quickly as they appear. However, during the violent stretching of inflation, something remarkable happened. These tiny, random fluctuations in energy density were caught by the expanding fabric of space and stretched to enormous, macroscopic sizes. Imagine a tiny wrinkle on the surface of a balloon. As you inflate the balloon to an immense scale, that tiny wrinkle becomes a vast, continent-sized fold. Inflation did exactly this to the quantum foam of the early universe. When the inflationary period ended, the universe resumed a more familiar rate of expansion. Those stretched-out quantum wrinkles, now imprinted as regions of slightly higher and lower density, became the seeds for all future structure in the cosmos. They are the very same density variations we see in the cosmic microwave background, the blueprint for galaxies. But here is where the path forks for primordial black holes. For most of these seeds, gravity worked slowly. It took hundreds of millions of years for them to pull in enough gas to form stars and galaxies. However, a small subset of these quantum wrinkles could have been exceptionally pronounced. If a region was dense enough by the time it re-entered what we call the cosmological horizon, the boundary beyond which light has not had time to reach us, it faced a dramatic choice. In the standard model, it would slowly begin to gather matter, but if its density crossed a critical threshold, it could have bypassed the slow collapse entirely. That ultra-dense packet of energy, a direct descendant of a quantum fluctuation, could have collapsed directly under its own immense weight, forming a black hole in an instant. This means primordial black holes are not just a wild speculation. They emerge as a natural, albeit speculative, consequence of our leading theory of the universe's earliest moments. If cosmic inflation is correct, then it almost inevitably produces these density variations. The question becomes not if some regions were extra dense, but whether any were dense enough to trigger direct collapse. This positions primordial black holes as a potentially testable prediction. Their existence or absence can give us feedback on the precise conditions during inflation, telling us about the landscape of energy in that first unimaginable fraction of a second. They become cosmic messengers from an era otherwise forever hidden from our view. But this hidden population of ancient black holes offers more than just a window into the past. They could be the key to solving one of the greatest mysteries in modern physics, the enigma of dark matter. For nearly a century, astronomers have known something is profoundly missing from our cosmic inventory. When we observe galaxies spinning or giant clusters of galaxies moving, the visible stars and gas simply do not provide enough gravitational glue to hold them together. The math does not add up. There must be a vast amount of unseen matter exerting a powerful gravitational pull, shaping the cosmos from the shadows. This invisible substance, which does not emit, absorb, or reflect light, is what we call dark matter. It makes up roughly 85% of all the matter in the universe. Its gravitational influence is the cosmic scaffolding upon which galaxies are built. Without it, our universe would look utterly different. Stars would never have gathered into the majestic structures we see today. For decades, the leading hypothesis has been that dark matter consists of a new, undiscovered type of particle. A prime candidate has been a theorized class called weakly interacting massive particles, or WIMP. These particles would be heavy by subatomic standards and interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. The search for WIMP has been one of the most ambitious and expensive endeavors in science, involving deep underground laboratories built to shield from cosmic rays, and vast arrays of sensitive detectors waiting for the elusive ping of a dark matter particle collision. Yet, after decades of searching, these sophisticated experiments have come up empty. No definitive signal has been found. This persistent silence has forced scientists to broaden their thinking. Could dark matter be something else entirely, something we have not been looking for in the right way? This is where primordial black holes re-enter the story with compelling elegance. Think about the basic profile of dark matter. It must be massive to exert such strong gravity. It must not interact with light, remaining completely invisible. And it must have been present in the early universe to guide the formation of the first galaxies. Primordial black holes check every one of those boxes. They are, by definition, massive concentrations of matter. They emit no light except for potential, incredibly faint quantum effects at their boundaries. And if they formed in the universe's first second, they were certainly present at the dawn of structure formation. They are, in essence, ready-made dark matter candidates. A population of these ancient gravitational knots, sprinkled throughout the cosmos, could provide the exact unseen mass needed to explain the rotation of galaxies and the bending of light in galaxy clusters. They would not require any new physics beyond Einstein's theory of gravity and our models of the early universe. The idea is stunningly simple. What if the missing 85% of matter is not a sea of exotic particles, but a hidden archipelago of frozen cosmic moments, black holes born from the birth cries of space and time? But for primordial black holes to truly solve the dark matter puzzle, they must fit into a very specific cosmic weight class. Not all sizes would work. The most compelling candidates are those with masses ranging from a small asteroid to a large planet. Imagine a black hole with the mass of Mount Everest, or one with the heft of the entire Earth, each compressed into a space smaller than a single atom. It is a mind-bending concept, but these asteroid-to-planet mass objects could be the perfect dark matter particle, just one we never thought to look for because it is not a particle at all. Their small size means they would not disrupt star systems or shred passing comets in obvious ways, allowing them to drift unseen through the galaxy. Yet their sheer numbers could add up to the immense gravitational influence we observe. This idea solves a major problem that plagues other dark matter theories. Our observations of the light elements created in the first few minutes of the universe, during Big Bang nucleosynthesis, place a strict limit on how much normal or baryonic matter exists. Baryonic matter is the stuff of stars, planets, and us, made from protons and neutrons. If dark matter were made of normal matter, it would have participated in those early nuclear reactions and altered the cosmic recipe of hydrogen and helium in a way we do not see. This is the genius of primordial black holes in this specific mass range. They are non-baryonic. They formed in the first chaotic instant before protons and neutrons even existed. They are knots of pure energy that collapse directly into gravity wells, bypassing the stage of being normal matter entirely. Therefore, they do not count against the baryonic budget. They are a separate shadow component that gravity sees, but the early nuclear furnace did not. This allows them to provide the missing mass without contradicting our most sacred measurements of the infant universe. Picture our galaxy not as a disk of stars surrounded by a diffuse halo of invisible particles, but as a disk of stars embedded within a vast spherical cloud of countless tiny black holes, each a frozen fragment of the Big Bang. This ancient swarm, numbering in the quadrillions, would weave through every part of the galaxy, including our own solar neighborhood. Their collective gravity would be the unseen hand that sculpts the rotation curves of galaxies and holds massive clusters together. All without the need for a single new fundamental particle. The universe may have provided its own dark matter solution in its very first moment, a gravitational echo waiting 13 billion years to be heard. Yet for all their promise, the universe itself has placed strict limits on this possibility. Primordial black holes cannot simply fill every conceivable mass and solve the dark matter mystery in one sweeping gesture. Over decades, astronomers have developed powerful ways to search for these invisible objects, not by seeing them directly, but by observing their subtle gravitational effects on the world of light. These searches have systematically ruled out vast swaths of potential mass, carving away at the idea. One of the most powerful techniques is called gravitational microlensing. The principle is elegant. If a compact, dark object like a primordial black hole passes directly between us and a distant star, its gravity will act like a lens, bending and focusing the star's light. From our perspective, the star will temporarily brighten, then fade in a characteristic curve. Massive, dedicated sky surveys like the Optical Gravitational Lensing Experiment, or OGLE, have spent years monitoring millions of stars, watching for these telltale flashes. Their results are clear. They have not seen nearly enough of these microlensing events to account for dark matter if it were made of black holes around the mass of Jupiter. That specific window is firmly closed. Other constraints come from the cosmic microwave background, that ancient snapshot of the infant universe. If a large number of primordial black holes were present when this light was released, their gravity and any material falling into them would have injected extra energy, subtly altering the background's temperature patterns in ways we do not observe. This rules out a dominant population of black holes in a range from about the mass of our Moon up to many thousands of solar masses. Even the dynamics of wide binary star systems in our galaxy argue against certain masses, as the gentle gravitational tugs of passing black holes would disrupt these fragile pairs over cosmic time. So where does this leave us? After all these observational tests, the landscape of possibility has been dramatically narrowed, but it has not been eliminated. Intriguing windows remain where primordial black holes could still constitute all, or a significant portion of the dark matter. The most compelling of these surviving windows lies at the very low end of the mass spectrum, in the realm of asteroid mass black holes. We are talking about objects with masses comparable to a large mountain or a small world, compressed into a space smaller than a single proton. This range, from about 1 billion tons to the mass of the Moon, has so far evaded the most stringent constraints. These black holes would be too light to create detectable microlensing events for current surveys, and their small size means their interactions with the early universe's plasma would have been minimal, leaving the cosmic microwave background untouched. They are the cosmic ghosts that could still be hiding in plain sight, a fine, gravitational dust woven through the fabric of space, collectively weighing more than all the stars and galaxies we can see. The hunt is no longer for a single, monolithic solution, but for a specific and elusive spectral signature, a whisper of gravity from the very first instant. The existence of these ancient black holes could solve another, seemingly unrelated cosmic enigma. Deep in the hearts of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole. These are not the stellar remnants we have discussed. They are incomprehensible monsters, weighing millions to billions of times the mass of our Sun. Their mere presence is a profound mystery, but the timeline of their appearance makes the puzzle almost paradoxical. With powerful telescopes, we can now look back over 13 billion years, observing the universe in its infancy. What we find is astonishing. Fully formed supermassive black holes, already weighing over 1 billion solar masses, are sitting in the centers of galaxies when the cosmos was less than 1 billion years old. To put that in perspective, that is like finding a 1,000-year-old tree in a forest that is only a decade old. Our standard models of black hole growth face an impossible race against time. In the traditional story, the first black holes would have been the remnants of the very first massive stars. These stellar black holes might have weighed a few dozen times the Sun's mass at most. From that modest seed, they would need to grow by voraciously consuming gas and merging with other black holes. But this process is not perfectly efficient. It generates intense radiation that can actually push material away, limiting how fast the black hole can feed. Even under ideal conditions, growing 1 billion solar mass giant from a stellar seed in under 1 billion years is an immense challenge, pushing the limits of known physics. It requires a feeding frenzy so extreme and sustained that many astrophysicists doubted could have happened so quickly, so universally, across the early cosmos. There is simply not enough time on the cosmic clock, so how did these titans get so big so fast? This is where primordial black holes offer a radical shortcut. Imagine if the starting point was not a tiny stellar remnant, but a ready-made heavyweight from the very beginning. Instead of a seed the size of a pebble, what if the universe planted an entire boulder? A primordial black hole formed in that first chaotic second could, in theory, have been born with a mass of 10,000 or even 100,000 suns. This is not a stellar corpse, it is a direct creation of the Big Bang itself. Such a massive seed changes the entire growth equation. With that kind of head start, a black hole has a much stronger gravitational pull from the outset, allowing it to draw in surrounding gas more effectively and rapidly. It does not need to spend hundreds of millions of years slowly building up from nothing. It begins its life as a significant gravitational anchor in the young universe. When the first clouds of gas began to condense to form a galaxy, this pre-existing heavy seed would naturally sit at the center, becoming the focal point for all subsequent growth. It is the difference between trying to build a castle by first making a single brick versus finding a fully constructed foundation already in place. This scenario elegantly bridges the gap in time. These primordial seeds scattered throughout the early cosmos could have quickly gathered the vast reservoirs of gas available in the dense infant universe, ballooning into the supermassive behemoths we observe at the dawn of time. They would not break the laws of physics, they would simply start the race much closer to the finish line. The presence of these ancient giants in young galaxies may not be a paradox after all, but a direct signature of the universe's explosive birth, a gravitational fossil pointing back to the very first instant. This possibility reshapes the very story of how galaxies came to be. The standard timeline relies on patient gravity, slowly amplifying tiny ripples over hundreds of millions of years. But if a hidden sea of primordial black holes was already present, the game changed immediately. These objects, regardless of their size, are pure concentrations of mass. From the moment they formed, they exerted a stronger gravitational pull than the smooth background of particles and radiation around them. They would have naturally begun to attract one another and to draw in the diffuse hydrogen and helium gas that filled the young cosmos. Crucially, they could start this clustering process long before the normal matter, hindered by the pressure of radiation, was able to collapse on its own. Think of the early universe not as a quiet, uniform soup, but as a landscape already dotted with deep, invisible wells of gravity. These wells served as prefabricated foundations, gravitational anchors waiting for the universe to cool enough for gas to fall into them. When that pivotal moment arrived, the effect would have been transformative. In the traditional model, the first protogalactic clouds had to build their own gravity wells from scratch, a slow and inefficient process. But with primordial black holes, the wells were already dug. Vast rivers of primordial gas would have streamed toward these pre-existing concentrations of mass, accelerating collapse at a breathtaking pace. The formation of the first dense, star-forming clouds could have been jump-started, shaving critical time off the cosmic dark ages. It is the difference between waiting for rain to slowly collect into puddles versus having a network of basins already in place to catch every drop the moment the storm begins. These early black holes would not have been passive inhabitants of the young cosmos. They would have been active architects, laying down the gravitational blueprint upon which the first luminous structures were built. Their influence might extend even further to the very shape and distribution of galaxies we see today. The largest primordial black holes, those born as massive seeds, would have naturally become the cores of the greatest future galaxies. Their immense early gravity would have drawn in phenomenal amounts of material, setting the stage for the rapid growth of supermassive black holes and the majestic ellipticals and spirals they anchor. Meanwhile, a widespread population of smaller asteroid mass black holes could have acted as a kind of gravitational glue within dark matter halos, helping to stabilize the first structures and influencing how they merged together over billions of years. This suggests our cosmic web, the great filamentary structure of the universe with its clusters and voids, might bear the subtle imprint of those first gravitational seeds. The story of our universe, from the tiniest dwarf galaxy to the largest supercluster, could be a story written not just by dark matter, but by the specific, ancient fingerprints of black holes born in the fire of creation. The search for these cosmic ghosts may require listening to the universe in an entirely new way. For most of human history, astronomy has been the study of light, from the visible stars to invisible radio waves and X-rays. But light can be blocked, scattered, or absorbed. Gravity, however, cannot. Every massive object that moves creates ripples in the fabric of spacetime itself, distortions that travel at the speed of light. These are gravitational waves. Their detection marked a revolution, opening a window onto a dark universe we could never see. Now, this new sense is becoming our most powerful probe for primordial black holes. When two black holes spiral inward and finally merge, they unleash a tremendous storm of gravitational energy, sending powerful ripples across the cosmos. Observatories like LIGO and Virgo are essentially giant microphones listening for these faint cosmic tremors. Each detected wave carries a unique signature, encoding the masses of the colliding objects and their distance from us. This data is a direct census of the black hole population in the universe, and it is here that the primordial hypothesis faces a critical test. If a significant number of black holes are primordial, born from the early universe rather than from dying stars, their mergers should leave a distinctive imprint in the gravitational wave data. Stellar black holes come from stars, and stars obey certain rules. They form from collapsing gas clouds and have masses that generally fall within a predictable range, up to maybe a few dozen times the mass of our Sun. There is also a theoretical upper limit, because a very massive star becomes so unstable it may blow itself apart completely, leaving no black hole behind. This creates what astrophysicists call a pair-instability mass gap, a range where stellar black holes should be very rare, roughly between about 50 and 120 solar masses. Primordial black holes, however, play by different rules. They are not born from stars, so they do not care about stellar physics. They could easily form within that forbidden gap or even far beyond it. A gravitational wave signal from black holes in this unexpected mass range would be a strong hint of a primordial origin. This is not just theory. In May of 2019, LIGO and Virgo detected an event named GW 190521. The signal revealed the merger of two black holes with final mass about 142 times that of our Sun. More intriguingly, the individual black holes that collided were estimated at about 85 and 66 solar masses. One of them sits squarely in that pair-instability gap where stellar black holes are not supposed to exist. The scientific community was electrified. Could this be our first direct evidence of a primordial black hole? It is a compelling possibility. The sheer mass of the objects challenges the standard stellar story, pointing toward an exotic origin. Furthermore, the rate of black hole mergers we observe could be another clue. If primordial black holes are abundant, acting as dark matter, they would occasionally find each other in the vastness of space and merge. The frequency of these events detected by LIGO and Virgo could tell us if there are enough of these ancient objects out there to account for the universe's missing mass. Every chirp and rumble from the gravitational wave observatories is not just a discovery, it is a potential message from the first second of time, a direct echo of the density fluctuations that shaped everything. The detection of gravitational waves has given us a new language for listening to the cosmos. Among the chorus of collisions, a few signals stand out as profound anomalies, whispers that defy our expectations and point toward something ancient. The event known as GW 190521 is perhaps the most famous example. When the ripples from this distant cataclysm reached Earth, scientists decoded a story of two black holes merging to form a final object about 142 times the mass of our Sun. The individual black holes involved were estimated at roughly 66 and 85 solar masses. It is this number, 85, that sent a ripple through the astrophysics community. According to our best models of how massive stars live and die, black holes should not naturally form in this range. This is the heart of the pair-instability mass gap. When a very massive star, between about 65 and 130 solar masses, reaches the end of its life, its core becomes so hot that the energy of light itself begins to create electron and positron pairs. This process robs the core of the pressure supporting it against gravity, leading to a runaway thermonuclear explosion. The star does not leave a quiet remnant. It is completely obliterated in a titanic supernova that leaves nothing behind. A black hole of 85 solar masses should not exist if it came from a single dying star. The star that could have birthed it would have been too massive to die quietly, and not massive enough to collapse past this explosive barrier. So the detection of an object in this gap is a direct challenge to standard stellar astrophysics. It is like finding a fossil of an animal that, according to all biological rules, should have never been born. This forces a question: if this black hole was not forged in the death of a star, where did it come from? The properties of the merger offer another clue. The event was relatively quiet, with the black holes showing little to no spin. In the standard model, black holes born from binary star systems often inherit the spin of their parent stars, like a dancer continuing a turn. The lack of significant spin in this event suggests these objects may not have had a stellar upbringing at all. Instead, they could have formed in the dark through a different process entirely. This is where the primordial black hole hypothesis steps in with a compelling explanation. Primordial black holes do not care about stellar physics or pair instability. They form from density fluctuations, not from stars. An 85 solar mass black hole is not a forbidden object in that early universe. It is simply a region of space that happened to be dense enough to collapse directly. If such objects were abundant in the early cosmos, they would naturally drift through space, occasionally finding each other. In the dense environments of dark matter halos or within ancient star clusters, two of these primordial black holes could be gravitationally drawn together over billions of years, eventually spiraling in and merging. This process would produce exactly the kind of signal LIGO detected: black holes of unexpected mass with minimal spin, merging in the emptiness of intergalactic space, far from the stellar nurseries we typically associate with black hole formation. GW 1905-21 is not alone. Other events, like GW 1904-12, involved a black hole of about 30 solar masses merging with an object in a lower mass gap, another region where stellar collapse faces theoretical hurdles. Each anomalous detection adds weight to the idea that our universe's black hole population is more diverse and more ancient than we ever imagined. These are not mere outliers, they are potential signposts pointing back to a time when the cosmos was writing its own rules and seeding itself with gravitational mysteries that would only reveal themselves 13 billion years later. While massive mergers grab headlines, the true nature of dark matter might be hiding at the opposite end of the scale. The hunt for primordial black holes has shifted its focus from stellar giants to planetary whispers, to objects with the mass of worlds. Here, a decades-long astronomical survey has uncovered a mystery that perfectly aligns with this ancient hypothesis. For over 30 years, the optical gravitational lensing experiment, known as OGLE, has been conducting a cosmic census. Using telescopes in Chile, it has meticulously monitored hundreds of millions of stars toward the dense central bulge of our Milky Way galaxy. Its primary tool is gravitational microlensing, watching for the subtle, temporary brightening of a background star when a dark, compact object passes directly in front of it. The duration and shape of that brightening tell a story about the mass and distance of the invisible lens. What OGLE has found is startling. The survey has detected a significant population of isolated, free-floating objects with masses in the range of Earth to Neptune. These are not planets orbiting stars, they are nomads drifting alone through the interstellar darkness. The immediate, conventional explanation is that these are rogue planets, worlds ejected from their native star systems during the chaotic gravitational dances of their youth. While some undoubtedly are, the sheer abundance of these events poses a problem. There seem to be too many of these isolated planetary mass objects to explain easily through planet ejection alone. It stretches our models of how planetary systems form and evolve. This is where the primordial black hole idea offers an elegant alternative. What if a fraction or even all of these microlensing events are not planets at all? What if they are asteroid-to-planet mass primordial black holes? An Earth mass black hole would be a sphere with a radius of only about 9 millimeters, smaller than a marble. A Neptune mass black hole would be roughly the size of a soccer ball. These unimaginably dense objects would produce an identical microlensing signature to a planet of the same mass. They would drift through the galactic halo, the vast spherical cloud of dark matter surrounding the Milky Way, completely invisible except for these rare, perfect alignments. The OGLE data does not tell us if the lens is a ball of rock or a knot of spacetime. It only tells us the mass is there. This creates a fascinating interpretive puzzle. The observed events could be a mix of both exiled planets and ancient black holes. Or, more provocatively, they could be predominantly black holes, with the primordial population accounting for a substantial portion of the dark matter halo's mass in this specific range. This would mean that dark matter holding our galaxy together is not a uniform particle mist, but a fine gravel of frozen quantum moments, each a tiny, perfect gravitational pit. The beauty of this idea is its testability. Future surveys, especially those from space telescopes free of atmospheric blur, will detect many more of these fleeting events. By analyzing their precise patterns, their distribution across the sky, and their correlation with known structures, astronomers may begin to statistically separate the two populations. If the distribution of these lenses follows the expected shape of the dark matter halo rather than the disk where most stars and planets reside, it would be a powerful clue. Every unexplained microlensing flash becomes a potential candidate, a tiny signal from a colossal past, waiting for its true identity to be revealed. But these ancient shadows may have left their mark on the universe's oldest photograph. The cosmic microwave background is our most pristine snapshot, a baby picture of the cosmos taken just 380,000 years after the Big Bang. Its near-perfect uniformity is a cornerstone of modern cosmology, yet within its subtle temperature variations lie potential fingerprints of primordial black holes, not as direct objects, but as sources of disruption in the infant universe. To understand this, we must picture the cosmos in its first few 100 million years. It was a dark, neutral sea of hydrogen and helium gas, still cooling from the fires of creation. If a significant population of primordial black holes was drifting through this sea, they would not have been passive. Their immense gravity would have acted like cosmic magnets, slowly pulling the surrounding gas toward them. As this gas spiraled inward, it would have compressed and heated up, just as air heats up when you pump it into a tire. Before plunging across the black hole's boundary, this heated gas would have glowed, emitting energy, particularly in the form of X-rays and ultraviolet light. This process is called accretion, and in the early universe, it would have been a widespread phenomenon if black holes were abundant. This injected energy is the key. That extra X-ray and ultraviolet radiation would not have stayed localized. It would have traveled out into the neutral hydrogen gas that filled the cosmos. When these high-energy photons struck a neutral hydrogen atom, they could rip the electron away from the proton, re-ionizing the gas. This means the universe, which had become neutral and transparent after recombination, would have begun to become a scattered, ionized plasma again in patches around each black hole. This messy reionization leaves a distinct signature on the cosmic microwave background. The free electrons created by this process would have scattered the SIMB photons one more time, subtly blurring the pristine temperature patterns we see and adding a specific type of polarization to the light. It is like trying to look at a detailed painting through a shower of fine rain. The image becomes slightly smeared. Scientists working with the Planck satellite, which mapped the CMB with exquisite precision, have searched for exactly this kind of blurring. They asked if primordial black holes made up all the dark matter, how much would they have heated and re-ionized the early universe? The answer from the data is clear: not that much. The observed CMB shows no evidence of the widespread early re-ionization that a dominant population of accreting black holes would have caused. This places extremely tight constraints, effectively ruling out the possibility that primordial black holes across a wide range of masses, from about the mass of our moon to many thousands of solar masses, could account for 100% of the dark matter. The cosmic baby picture is too clean, too undisturbed to allow for that level of early chaos. However, this is not the end of the story. The constraints are powerful, but they are not absolute vetoes. They leave open fascinating possibilities. A sub-dominant population of primordial black holes could still exist, contributing a fraction of the dark matter without overheating the early universe beyond what the CMB allows. Alternatively, black holes at the very lowest mass ranges, like asteroid mass black holes, are so tiny that their accretion and energy output would have been negligible, leaving the CMB untouched. Or the early gas might have been too hot and diffused to fall efficiently into the black holes, limiting their accretion power. The CMB data does not erase primordial black holes from the cosmic ledger. It simply tells us they could not have been the only actor on the stage. They must share the dark matter role with something else, or exist in numbers modest enough to stay hidden in the noise of the universe's first light. This forces a more nuanced view, where the answer to our cosmic mysteries may not be a single elegant solution, but a complex choir of different phenomena singing together. The final moments of a black hole's life offer another path to finding these ancient relics. Stephen Hawking made one of the most startling predictions in modern physics, that black holes are not completely black. Through a subtle quantum effect at their boundary, they can slowly leak particles and energy, a process now called Hawking radiation. This radiation causes the black hole to lose mass and over immense timescales evaporate entirely. For the black holes we know, this process is so slow it is practically a footnote in cosmic history. A stellar black hole with the mass of our Sun would take many, many times the current age of the universe to evaporate, a number with over 60 zeros. For the supermassive giants at galactic centers, the timescale is so staggeringly long it is essentially forever. But this equation changes dramatically for the smallest possible black holes. Hawking radiation's intensity is inversely related to the black hole's mass. The smaller the black hole, the hotter it glows and the faster it evaporates. This leads to a fascinating possibility for our search. If primordial black holes were formed with very low masses, say smaller than a large mountain, their entire lifetime could be shorter than the age of the universe. They would not be drifting quietly in the darkness today. They would have already reached the end of their lives, and their end would not be a quiet fade, it would be a spectacular flash. As a tiny black hole loses mass, it heats up, radiating faster and faster in a runaway process. In its final second, it would release a tremendous burst of high-energy gamma rays, a final explosive signature of its existence. This transforms the search from looking for invisible gravitational anchors to scanning the sky for the last brilliant sparks of dying cosmic embers. Astronomers have searched for these telltale gamma-ray bursts from evaporating primordial black holes. While no definitive signal has been found, the absence of such explosions also tells us something, placing limits on how many of these very low-mass black holes could have populated the early cosmos. It is a profound thought that the universe's first moments might be marked not only by silent creation, but by the fading echoes of countless miniature explosions, each a quantum farewell from a fragment of the Big Bang itself. These final, brilliant flashes could be hiding in plain sight among the most energetic signals we detect. For decades, astronomers have catalogued brief, intense eruptions of gamma rays from across the cosmos, known as gamma-ray bursts. The longest of these are linked to the catastrophic deaths of massive stars, but a subset, the short gamma-ray bursts, lasting less than 2 seconds, are more enigmatic. They are often attributed to the collisions of ultra-dense objects like neutron stars. Yet, within this catalogue of cosmic fireworks, there may be a different kind of signature entirely. Some of these fleeting, unexplained flashes could be the death cries of the smallest primordial black holes. Picture a black hole with the mass of a large mountain, a relic so tiny it has spent nearly the entire age of the universe slowly evaporating through Hawking radiation. In its final moment, this process would accelerate violently. The black hole would not fade away, it would effectively explode, converting its remaining mass into a torrent of high-energy particles and radiation. The signature would be distinct, a solitary, incredibly sharp spike of gamma rays. Unlike a neutron star collision, which might produce a longer, messier afterglow across other wavelengths, the death of a tiny primordial black hole would be a clean, isolated event. It would be a flash without a source, a burst with no visible host galaxy because the black hole could be drifting in the emptiness between stars. The energy spectrum of the photons would also carry clues, potentially matching the theoretical predictions for a black hole's final quantum evaporation. While no event has been definitively matched to this profile, the search continues. Every time a satellite like NASA's Fermi Gamma-Ray Space Telescope detects a short, orphan burst with no obvious explanation, it adds a data point to this cosmic mystery. Finding even one would be a monumental discovery. It would provide direct evidence not only for Hawking radiation, a profound quantum gravitational effect, but also for the existence of black holes forged in the universe's first instant. It would mean that the echoes of creation are not just silent gravitational wells, but occasional, brilliant sparks, the last whispers of a world that existed before atoms, before stars, before light itself had a path to travel. This transforms the entire quest from a simple search for dark matter into something far more profound. The first instants after the Big Bang were not merely a prologue, they were the ultimate physics experiment. Conditions existed there that we could never hope to recreate, energies so extreme they make our most powerful particle colliders seem like gentle toys. In this sense, the early universe itself becomes our most advanced laboratory, and primordial black holes are the sensitive instruments it left behind. Their very existence or absence is a direct report from the frontier of reality. To form a primordial black hole, a region of space needed to be exceptionally dense compared to its surroundings. The degree of that density contrast is not arbitrary, it is a precise measurement. It tells us about the strength of the quantum fluctuations that were stretched during inflation. Think of it like this: if the early universe was a stormy sea, the height of the waves, those density contrasts, was determined by the ferocity of the inflationary wind. By searching for black holes of specific masses, we are essentially measuring the height of the waves that crashed during the universe's first second. A detection would give us a number, a data point from an energy scale 1 trillion times higher than what the Large Hadron Collider can probe. This data could distinguish between competing models of cosmic inflation. Some theories predict many pronounced density peaks, leading to a rich population of primordial black holes. Others predict a smoother ride, resulting in far fewer. By observing the mass spectrum of these ancient objects, we are reading the fine print of inflation's contract with the cosmos, but the implications reach even further. The transition out of that inflationary state might not have been smooth. Theorists suggest the universe could have undergone dramatic phase transitions, akin to water suddenly freezing into ice. Such violent shifts in the fabric of reality could have created shockwaves, regions of intense density that readily collapsed into black holes. Finding a population of black holes with a very specific, narrow range of masses could be the smoking gun for one of these cosmic upheavals, a fossilized record of the moment the universe changed its state. More speculatively, some models of string theory and quantum gravity suggest our universe has more than the three spatial dimensions we experience. In the first moments, these extra dimensions could have been compactified or curled up on themselves. The process of that curling could have created topological defects, knots in spacetime, that themselves collapsed into black holes. If we found black holes with properties that defy all other explanations, they could be our first experimental hint of these hidden dimensions, a gravitational message from the full geometry of reality. So every microlensing event, every anomalous gravitational wave chirp, is not just an object. It is a piece of data from the highest energy experiment ever run, an experiment that began 13.8 billion years ago and whose results are only now drifting into our detectors. We are not just hunting for dark matter, we are conducting archaeology on the laws of physics themselves, using gravity as our trowel to uncover how the universe truly began. This search for ancient gravitational whispers forces us to confront the very mechanism that may have created them. The theory of cosmic inflation, our best explanation for the universe's smoothness and structure, faces a subtle but profound challenge from primordial black holes. To understand why, we must look at the numbers. The density fluctuations we see imprinted on the cosmic microwave background are remarkably small, just about 1 part in 100,000. These gentle ripples were perfectly sufficient to seed the galaxies and clusters we see today through slow, gravitational growth. However, to create a primordial black hole, you need a much more dramatic event. A region of space needs to be so extraordinarily dense that it collapses directly under its own weight, bypassing billions of years of cosmic evolution. The required density contrast is not 1 part in 100,000, but closer to 1 part in 2 or 3. It is the difference between a gentle hill on the landscape and a sheer, towering cliff. If primordial black holes exist in any significant number, it means the story of inflation cannot be a simple, smooth expansion. That early period of hypergrowth must have included moments of dramatic intensity, where the quantum fluctuations being stretched were not uniform whispers but occasional shouts. This forces cosmologists to refine and test specific models of inflation, moving from a general concept to detailed blueprints of the universe's first moment. The standard, simplest models of inflation tend to produce a very smooth spectrum of fluctuations, all roughly the same size. They are excellent at making the gentle hills that became galaxies, but terrible at making the sharp cliffs that could become black holes. So if we find evidence for these cliffs, we must look to more complex inflationary scenarios. One compelling idea involves a feature often called a plateau or an inflection point in the inflationary energy field. Imagine the process of inflation as a ball rolling slowly down a gentle hill. For most of the journey, the ball rolls smoothly, stretching space and creating those small, uniform quantum ripples. But what if partway down the hill temporarily flattened out or even developed a small dip? The ball's roll would slow dramatically during that plateau. In the language of physics, this slowing would amplify the quantum fluctuations being generated at that specific moment. It would take those tiny quantum whispers and magnify them into much louder signals. When inflation later ended and the universe transitioned to its familiar expansion, those amplified fluctuations would exist as ultra-dense regions sprinkled throughout the cosmos, prime candidates for direct collapse into primordial black holes. Another model introduces a sudden step or a phase transition during inflation. Think of it as the ball rolling down a hill that has a single, sharp downward bump. Crossing that bump would create a brief burst of energetic turbulence, again enhancing fluctuations in a specific range of scales. These are not just mathematical curiosities. Each distinct model, the plateau, the step, and others, predicts a specific signature. It would produce primordial black holes with a characteristic mass distribution, a particular fingerprint in their numbers and sizes. For instance, a plateau might generate a narrow peak of black holes all within a specific mass range, like a cosmic factory producing one model of gravitational relic. A different mechanism might produce a broader spectrum. This is why the hunt for primordial black holes is so revolutionary. It is not merely about finding objects, it is about using them as diagnostic tools. A confirmed detection, especially with a measured mass distribution, would act as a cosmic voting ballot between competing theories of inflation. It would tell us which detailed blueprint most accurately describes the universe's explosive birth. The gentle hills we see in the cosmic microwave background give us the broad strokes of the story, but the potential cliffs in the form of black holes would reveal the dramatic subplot, the moment when the rolling ball hesitated, and in that pause sowed gravitational seeds directly into the fabric of reality. The implications of these ancient objects stretch beyond the boundaries of our observable cosmos into the realm of the profoundly speculative. Some of the most ambitious theories in physics suggest our universe may not be alone. Concepts like eternal inflation and the string theory landscape propose that what we call the universe is just one expanding bubble in an infinite, frothing sea of reality, a vast multiverse. Each of these bubble universes could have its own unique laws of physics, its own constants and dimensions forever separated from our own. If such a multiverse exists, its signature might be written in the gravitational fossils we have been discussing. In the chaotic first moments of our bubble's expansion, it is possible it brushed against another. A collision between two infant bubble universes would have been an event of unimaginable energy, a cataclysm on the scale of creation itself. Such a titanic impact would have sent violent shockwaves rippling through the fabric of our newborn cosmos. These shockwaves would have created regions of spacetime with immense, concentrated density. And what happens in the early universe when you have a region of extreme density? It becomes a prime candidate for direct collapse into a primordial black hole. In this extraordinary view, detecting a population of primordial black holes with a specific, unexpected distribution of masses could be more than just evidence for an early cosmic event. It could be a relic of that long-ago collision with another reality, a cosmic bruise from a meeting with a neighbor we can never otherwise see. The philosophical shift here is staggering. We are used to asking questions about the origin and fate of our universe, but if primordial black holes carry this signature, we would be forced to ask a different question entirely. Which universe? Their detection could become our first indirect, tentative evidence that our cosmic home is part of a far grander, perhaps infinite, ensemble. It would mean the deepest mysteries of our existence might not be solved by looking inward at our own cosmos, but by recognizing the subtle, gravitational scars left by a reality beyond our own. While cosmic inflation provides the leading framework, the potential for primordial black holes extends far beyond a single theory. The early universe was a cauldron of extreme physics, and any process that created intense, localized density could have seeded these gravitational fossils. One compelling alternative involves cosmic strings, hypothetical remnants from the universe's symmetry breaking phase transitions. Picture the early cosmos cooling from an ultra-symmetric state, like water freezing into ice. As it cooled, the fundamental fields that govern reality could have settled into different configurations in different regions. Where these domains met, topological defects might have formed, not flaws but stable, persistent structures woven into spacetime itself. Cosmic strings are theorized to be such defects, unimaginably thin filaments of energy thinner than a proton, but with the mass of a mountain range per inch, stretching across cosmic distances. Their gravity would be immense. If two such strings crossed or a loop of string collapsed, the concentration of energy at that intersection could be so extreme it would crumple spacetime itself, directly birthing a primordial black hole. These would not be born from quantum wrinkles, but from the tangled geometry of the cosmos settling into its current form. Another pathway lies in the collapse of domain walls. If the early universe's phase transitions created not one-dimensional strings, but two-dimensional sheets separating regions of different field values, these domain walls would have been phenomenally dense. Under their own gravity, a large enough wall could become unstable and fragment, with each collapsing fragment potentially forming a black hole. The scale here is dramatic, potentially creating black holes across a wide mass range from small to surprisingly large. Then there are the transitions themselves. As the universe expanded and cooled, it likely passed through several critical thresholds where the behavior of matter and energy changed fundamentally. One of the most significant is the quantum chromodynamic, or QCD, transition. This occurred when the universe was just a few microseconds old, the moment when the primordial quark gluon plasma condensed into the protons and neutrons that would later build atoms. During this shift, the equation of state of the universe, the relationship between its pressure and density, softened momentarily. This brief period of reduced pressure resistance made it easier for any existing density fluctuations to collapse. It effectively lowered the threshold for black hole formation. If there were modest overdensities present at that exact cosmic instant, the QCD transition could have given them the final nudge into collapse, potentially producing a distinct population of black holes with masses around that of a large asteroid, a mass scale intriguingly linked to some dark matter candidates. What these diverse mechanisms highlight is a profound truth. Primordial black holes are not merely a prediction of one specific model of inflation. They emerge as a generic, almost inevitable possibility in many extensions of our standard physics. Whenever we push our theories into the extreme conditions of the first instance, processes that concentrate mass and energy frequently lead to gravitational collapse. This makes them a powerful unifying target. Searching for these ancient objects is not a test of a single idea, but a probe into the entire landscape of high-energy physics and cosmology. Their discovery, and crucially, the measurement of their mass distribution, would act like a cosmic fingerprint. That fingerprint could tell us which of these many theoretical pathways our universe actually took. Did we form from amplified quantum fluctuations, from the snapping of cosmic strings, or from the shudder of a phase transition? Each leaves a different mark. The black holes themselves become the final evidence, the durable data from experiments that concluded in a fraction of a second, over 13 billion years ago. The hunt for these cosmic ghosts may not require telescopes pointed at distant galaxies. It might lead us to our own celestial backyard, to the dark, frozen fringes of our solar system. For decades, astronomers have tracked the distant, icy objects that orbit far beyond Neptune, in a region known as the Kuiper Belt. The motion of some of these trans-Neptunian objects holds a curious anomaly. Their orbits appear strangely clustered, as if an unseen hand is gently shepherding them, tugging them into similar alignments. The gravitational pull of the known planets cannot account for this pattern. This has led to the long-standing hypothesis of Planet 9, a hypothetical world several times the mass of Earth, orbiting in the profound darkness. But what if the shepherd is not a planet at all? What if it is a primordial black hole with the mass of Earth or Mars, but compressed into a space smaller than your palm? This is a speculative yet profoundly intriguing possibility. Such an object would be the ultimate dark planet. It would emit no light, reflect no sunlight, and be detectable only by the subtle warping it imprints on the paths of everything that passes nearby. Its gravitational signature would be identical to that of a planetary mass object, perfectly mimicking the proposed Planet 9. The difference is not in the gravity, but in the nature of the object causing it. One is a frozen world of rock and ice. The other is a frozen knot of space-time from the dawn of creation. Imagine the implications. A relic from the universe's first second could be orbiting in our own solar system, a permanent, invisible neighbor that has been here since the sun and planets formed. Its presence would have shaped the architecture of our outer solar system over billions of years, gently sculpting the orbits of distant ice dwarfs through its persistent, silent pull. How would we find such an object? We could not see it, but we could sense its shadow. Future missions designed to map the outer solar system in extreme detail could look for the telltale signs. As this black hole drifts through its immense, slow orbit, it would occasionally pass in front of distant stars. Unlike a solid planet which would block the starlight entirely, a black hole would not. Instead, its gravity would lens the starlight, causing the star to temporarily brighten and distort in a specific, calculable way. A survey sensitive enough to detect these microlensing events within our own solar system could potentially pinpoint its location. Alternatively, precise tracking of spacecraft as they journey beyond Pluto could reveal minute anomalies in their trajectories, tiny deviations caused by the gentle tug of a hidden mass. Finding a primordial black hole here would be a discovery of unparalleled significance. It would solve the orbital mysteries of the outer solar system, yes. But more than that, it would deliver a pristine specimen of the early universe right to our doorstep. We would have a direct, tangible target for study, a chance to observe the gravitational effects of a black hole in unprecedented detail, and definitive proof that our cosmic neighborhood was built with ancient, invisible stones. The coming decade will witness an unprecedented assault on this cosmic mystery. We are entering a golden age of observational astronomy, where a new generation of instruments, each more sensitive than the last, will turn speculative whispers into hard data. These campaigns are not merely upgrades, they are revolutions in how we perceive the dark universe, and they are poised to deliver a definitive verdict on the primordial black hole hypothesis. The first frontier is the realm of gravitational waves. Ground-based detectors like LIGO and Virgo have opened our ears to the cosmos, but they listen to a specific range of frequencies, like hearing only the deep bass notes of a symphony. To hear the full composition, we need to expand our hearing. Enter LISA, the Laser Interferometer Space Antenna. Scheduled for launch in the mid-2030s, LISA will be a constellation of 3 spacecraft flying in a giant triangular formation, millions of kilometers apart. Free from the seismic noise of Earth, it will detect gravitational waves at much lower frequencies. This will open a window onto mergers of monstrously massive black holes, the kind that could be primordial seeds as they spiral together in the early universe. It could also hear the gentle chirp of much smaller, asteroid mass black holes as they merge, a signal completely invisible to current ground-based observatories. On the ground, the proposed Einstein telescope will push sensitivity even further. Envisioned as a subterranean triangular observatory with 10-kilometer-long arms, its advanced design could detect black hole mergers from the very edge of the observable universe, providing a complete census of black holes across cosmic history. The statistical patterns in this data, the masses and the rates, will be the ultimate fingerprint, revealing whether the black hole population matches the slow story of stellar death or the explosive signature of primordial birth. In tandem, our eyes on the sky will grow exponentially sharper. The Nancy Grace Roman Space Telescope, set to launch by 2027, will conduct a microlensing survey of staggering scale. While current surveys like OGLE monitor millions of stars, Roman will watch hundreds of millions with exquisite precision toward the galactic bulge and beyond. It will catch those fleeting brightenings caused by invisible lenses with unparalleled clarity. Crucially, Roman will be able to measure an effect called parallax, using Earth's motion around the Sun to triangulate the distance to the lensing object. This will allow scientists to distinguish between a nearby rogue planet and a distant, ancient black hole drifting in the galactic halo. It could finally resolve the mystery of those isolated planetary mass events, telling us if they are exiled worlds or fragments of the Big Bang. Our view of the ancient universe will also crystallize. Next-generation experiments like the Simons Observatory and CMB Stage 4 will map the cosmic microwave background with microscopic detail, searching for the faintest smudges of early reionization or subtle spectral distortions that could betray the presence of accreting black holes in the cosmic dawn. These maps will push constraints on primordial black holes to their absolute limits, potentially ruling out even subdominant populations across wide mass ranges. Meanwhile, monitors of the high-energy sky will grow ever more vigilant. Future gamma-ray observatories with larger collecting areas and faster response times will scan for the unique, solitary flash of an evaporating black hole's final moment. A confirmed detection would be an instant landmark, proving both Hawking radiation and the existence of these tiny relics in one brilliant burst. The convergence of data from these disparate realms, the ripples in space-time, the warping of light, the pristine ancient glow, and the flash of high-energy death creates a powerful web. A signal seen in one channel must be consistent with the silence or confirmation in the others. Within the next 10 to 15 years, this collaborative detective work will reach a conclusion. Either we will find the unambiguous signature of primordial black holes, rewriting our cosmic origin story in real time, or we will systematically close the remaining windows of possibility, consigning this elegant idea to the history of beautiful theories slain by ugly facts. The universe has held its secret for 13.8 billion years. Our tools are finally catching up to the question. This convergence points toward a profound philosophical shift in how we understand our cosmic story. For decades, dark matter and supermassive black holes have been treated as separate, monumental puzzles. One is the invisible glue holding galaxies together. The other are the incomprehensible giants at their hearts. Entire fields of physics have grown around each mystery, often working in parallel, searching for distinct solutions in particle accelerators and telescope data. But the primordial black hole hypothesis offers a breathtakingly different perspective. What if these two great mysteries are not separate at all? What if they are different manifestations of the same ancient event? This is the promise of a truly unified explanation. The dark matter halos enveloping galaxies could be vast clouds of asteroid mass black holes, while the supermassive black holes at galactic centers could be the rare, heavyweight seeds that grew from that same primordial population. Both would share a common birth certificate stamped in the first chaotic second of the universe. Instead of needing two complex, independent stories, one for an unknown particle and another for impossibly fast black hole growth, we could have a single, elegant narrative. The violent density fluctuations of the infant cosmos did not just plant seeds for galaxies, they also sowed the entire spectrum of gravitational anchors, from fine dark matter dust to massive central stones, in one explosive instant. This represents a dramatic simplification of our cosmological model, an Occam's razor cut through decades of complexity. It suggests that the universe, in its first moment of existence, provided its own solutions, weaving the answers to its future mysteries directly into the fabric of spacetime. The search for these ancient objects, then, is not just about finding black holes. It is a quest to see if the cosmos speaks in a simpler, more unified language than we ever dared hope. A language where gravity itself, born from the chaos of beginning, wrote the story for everything to come. Yet for all their promise, primordial black holes are not the only contenders in this cosmic mystery. For decades, the dominant approach to dark matter has searched for answers not in macroscopic objects, but in the realm of the subatomic. Two leading particle candidates have defined this quest, each born from a different puzzle in fundamental physics. The first are WIMP, or weakly interacting massive particles. Their theoretical appeal was profound. They emerged naturally from popular extensions to the standard model of particle physics, like supersymmetry. WIMP would be heavy, slow-moving, and interact only through gravity and the weak nuclear force, making them perfectly invisible yet capable of clumping into the halos we observe. For years, they were the favored solution, leading to a global array of exquisitely sensitive detectors buried deep underground, waiting for the rare recoil of a WIMP striking an atomic nucleus. The second candidate is the Action, a hypothetical particle conceived to solve a completely different problem, the strong CP problem in quantum chromodynamics. Actions would be incredibly light, billions of times lighter than an electron, and behave more like a pervasive, oscillating field than a discrete particle. They would be produced in vast numbers in the early universe, flowing through space like a ghostly cosmic tide. Detecting them requires not underground tanks, but powerful magnetic fields designed to convert these elusive actions into faint microwave photons. The experimental journeys for both have been epic, pushing the boundaries of human ingenuity. Yet, the results have been a story of increasing silence. After years of data, the sophisticated WIMP detectors have found no conclusive signal, steadily ruling out vast swaths of their possible mass and interaction strength. The Action hunt, while younger, has also yet to report a definitive discovery. This persistent absence does not disprove these particles, but it has undeniably loosened their grip on the imagination of physicists, opening the door for more radical alternatives. We now stand at a pivotal crossroads. The next decade is setting the stage for a grand showdown between two fundamentally different visions of reality. On one side is the particle paradigm, the long-standing belief that the universe's missing mass is made of new, fundamental ingredients waiting to be discovered in the quantum realm. On the other is the gravitational, almost architectural paradigm of primordial black holes, which suggests the answer is not a new particle, but an ancient structure, a fossil of spacetime itself. This is more than a technical debate. It is a clash of philosophies about how the cosmos built itself. The experiments now coming online will serve as the ultimate arbiter. Will our telescopes and gravitational wave observatories find the unmistakable signature of ancient black holes? Or will our most sensitive particle detectors finally hear the whisper of a WIMP or an Action? The outcome will do more than solve the dark matter riddle. It will fundamentally direct the future of physics, determining whether the next great breakthrough lies in the domain of quantum fields or in the gravitational archaeology of the universe's first moment. And there is a fascinating third path, a hybrid model where both ideas share the stage. Perhaps dark matter is not a single entity, but a cosmic cocktail, a mixture of actions and asteroid mass black holes, each contributing to the gravitational tapestry. The universe has never been obliged to give us a simple answer. It may be that the full story requires us to listen to both the quantum whisper and the gravitational echo, to understand that the darkness is filled with more than one kind of ghost. From a speculative thought experiment to a cornerstone of modern cosmology, the journey of primordial black holes is a testament to science's relentless curiosity. What began as a theoretical possibility, a ghost in the equations of the early universe, has transformed into a serious and testable hypothesis with the power to connect our deepest origins to the cosmos we observe today. This idea elegantly threads together mysteries that once seemed separate, suggesting that the dark matter halos enveloping galaxies and the supermassive giants at their hearts might both be legacies of the same violent birth. The universe may have provided its own solutions in its first unimaginable instant, weaving the answers into the fabric of space-time as gravitational fossils. We now stand at a pivotal moment, where advanced telescopes and gravitational wave observatories are no longer just instruments of discovery, but tools of cosmic archaeology, digging for the fingerprints of creation itself. This search exemplifies how science truly progresses, not by blindly defending our established stories, but by actively seeking out the cracks and inconsistencies within them. It is in those cracks that we find the light of new understanding, the quiet persistence of a few unanswered questions, the orbital oddities in our solar system, the anomalous chirps from colliding black holes. These are not failures of our theories, but invitations to look deeper. The quest for primordial black holes is a direct response to that invitation, a promise that our cosmic origin story is not yet fully written. The next chapter will be decided not in the realm of pure theory, but in the data streaming in from the frontiers of observation. Within the coming years, as new surveys map the sky and new detectors listen to the ripples in space-time, we will have our answer. Will we find the ancient shadows, or will we close the final window on this elegant idea? Either outcome reshapes our understanding. To follow this search is to witness a fundamental piece of our universe's history being decided in real time. A reminder that the greatest stories are those still being uncovered, written in the silent language of gravity across the expanse of time.